This tutorial will discuss proteins and amino acids. Protein molecules, compared with the many other compounds we've studied, are in comparison ginormous. It's just gigantic. Proteins in a body are polymers made of 20 different amino acids. They differ in characteristics and functions that depend on the order of amino acids that make up the protein. The proteins form structural components such as cartilage, muscles, hair, and nails. And they function as enzymes to regulate biological reactions such as digestion and cellular metabolism. Hemoglobin and myoglobin transport oxygen to the blood. So here are the different classifications of proteins: structural, contractile, transport, storage, hormone, enzyme, protection. And these are just some examples. For instance, collagen and keratin you might see a lot in beauty products, and those are structural. Those are for like tendons and cartilage or hair. Hemoglobin, lipoproteins are transport. We just mentioned that hemoglobin transports oxygen. Amino acids are the molecular building blocks of the proteins. They have a central carbon atom called the alpha carbon, bonded to two functional groups, the amino group and the carboxylate group. They have a central carbon atom bonded to a hydrogen atom and an R group. Notice that we have four different things coming off of the carbon. We talked about this in previous tutorials. This is what we call a chiral carbon or a chiral compound, and they're stereoisomers. So let's focus on that R group. When you see the term R group, that simply means any generic carbon-containing group. It's an abbreviation that chemists use. If it's nonpolar, when it doesn't have any kind of electronegativity in there to draw the electrons in it, and when that happens, you have a nonpolar hydrocarbon side. These are considered hydrophobic, and it's referring to the water. And we talked about at length different ways in which the water interacts with the other molecules, and it always comes down to whether or not there's a positive negative interaction. Well, if it's nonpolar, there's no positive and negative there, and because of that it can't interact with the water. They refer to this as hydrophobic. In other words, it's scared of water. It doesn't want to be near the water. Hydrophilic is the opposite. Philic means love. It loves water. It likes to interact with the water. Therefore, it's going to dissolve in water. And this is because there's a polarity here. Notice in this particular one, there's an oxygen and nitrogen. Both of those are more electronegative. Therefore, the electrons are going to drift towards it, and you're going to have a positive side and a negative side. So here are the nonpolar amino acids. Notice in order for that to happen, it has to be a hydrogen or an alkyl group, or even an aromatic. While we're on this slide, I want to take a second to look at compare these R groups. There's only one R group here that's not chiral, that's achiral. This here is achiral. All the rest of these are chiral. The reason why this one's achiral is because you have two hydrogens on it. All the rest of them have four different things on it. An amino acid is polar when the R group is an alcohol, thiol, or amide. That's because of the extra electronegativity that these atoms become. And so the electrons are going to start drifting towards those electronegative areas, creating a positive and negative. Because of that positive negative, it's going to interact with water, which is why you get the term hydrophilic. All amino acids, once again, has an NH3, a COO, and an H. the amino acids differ by the R groups. An amino acid is acidic if the R group is a carboxylic acid. So here, ordinarily, we would have the COOH. So then that hydrogen is given up to make carboxylate. An amino acid is basic if the R group has an amine, which means it can absorb a hydrogen with that lone pair it has. Identify each of the following amino acids as polar or nonpolar. Well, here's your NH3 group and here's your COO group, carboxylate group. Well, we have two hydrogens. We have no area here for electronegativity outside of the carboxylic acid, and we don't consider that. So therefore, this is nonpolar. Here's our R group here. An OH group here. Because of that oxygen, that's creating a region of polarity. All the amino acids except for glycine are chiral. I mentioned that before because glycine is the only one where the H group is a hydrogen, which is the same as here. Alright, so let's take a look at how we did the chiral L and D classifications when we were using it with carbohydrates. We had the aldehyde at the top, and then we looked at the last chiral carbon, and we looked at the OH. If it was on the right, it was a D. If it was on the left, it was the L. We're going to do the exact same thing for the amino acids, except instead of having an aldehyde at the top, we have the carboxylate ion on the top. Because remember, the most electronegative thing, the most oxidized thing, goes on the top. Alright, so we look at the last chiral carbon, which is right here. We're going to look at the NH3 this time rather than the OH to determine if it's L or D. If it's on the left, it's L. If it's on the right, it's D. The carboxylate's on top. It's on the left, it's L. On the right, it's D. And that's your introduction to amino acids.